Now recall that a basis for a vector space or for a subspace is actually a set of vectors. So you have a bunch of vectors that have to obey two rules, two conditions. The first condition is that those vectors, they need to be linearly independent. And the second condition is that those vectors need to span the subspace or the vector space that you're considering. So those are the two conditions that we need to check. So here's the definition of basis right there. You have a bunch of vectors, finite number of vectors. They're vectors of V, okay? Then we say that those vectors form a basis for V if they obey these two conditions. If they are linearly independent and if the set spans the whole space. Now in example 4, on page 223, we have this example that shows 4 vectors in P3. Now remember P3, set of polynomials of degree 3 or less. We want to show that S is a basis for P3. So let's go ahead and check those two conditions. The first condition is that S is linearly independent. So to do that, we use the standard way of doing it. We set a linear combination of those vectors. We set that equals to 0, equals to the 0 vector. Now it turns out that the 0 vector in P3 is the polynomial 0, okay? It's the polynomial that is identically equal to 0. So let's go ahead and put 0 here. So that means I get this nice linear combination, or it looks like a regular polynomial of degree 3 and equals to 0. Now since the polynomial is identically equals to 0, then the only solution for those coefficients is that they need to be all 0. So C1 equals to C2 equals to C3 equals to C4, they're all 0. Okay. Now let me just put here just a small explanation why maybe you're being confused with this, but here's an example of a polynomial of degree 2. Let's say I have ax squared plus bx plus c equals to 0, okay? Now, if I say that this is identically equals to 0, if this is the 0 polynomial, then I'm saying that no matter what x is, this needs to be 0. That's what I'm saying here. And we want this whole thing here to be equals to 0. It doesn't matter what x is. We're not solving for x. We're not solving this equation for x. We're solving for the coefficient. So x can be anything. Actually, this relation here needs to be satisfied for all x's. So it's different here. Here we don't. If we want to find a, b, c such that this is true for any x. Okay, so remember, we're not solving for x, we're solving for a, b, c. Well, then the only possibility is that a needs to be equal to 0, and b needs to be equal to 0, and c needs to be equal to 0. That's the only way that this can be satisfied, okay? So that's why it's the same case here, but this is just for a third-degree polynomial, but it's the same thing. This can only be satisfied for any x if the c1, c2, c3, c4 are all 0, okay? We're not solving for x, we're solving for the c's. So that shows that those coefficients need to be 0, and that therefore the vectors 1x, x squared, and x cubed are linearly independent. Now the second thing we need to show is that those vectors span P3, but this is pretty obvious, right? So how do we show that span of 1x, x squared, x3 is P3? Well, that's pretty obvious, because if you pick any vector in P3, let's say pick a vector u, okay, in P3. Well, if it's in P3, then it's a polynomial of degree 3 or less. So u is actually a polynomial. It will be a plus bx plus cx plus dx. Oh, I forgot to put the square and the cube here, right? So u is actually a polynomial degree 3 or less. It could happen that the b here is 0, but anyway, it's in P3. Well, look at this. This is exactly a linear combination of those 4 vectors. Okay, so U is actually a linear combination of 1, x, x squared, x cubed. So any vector here is in P3, and obviously any vector in the span, because it's a linear combination of those vectors, they're also in P3. So these two are equal. In other words, those 4 vectors span P3. Now I'd like to show you, let's go back here to the original slide, or the original page here, first page. So that's an example of a non-standard basis. The next thing I would like to show you is theorem 4.9. This is a very interesting theorem. It shows that if you represent any vector in the space as a linear combination of vectors in the basis, then that representation is unique. So what do I mean by that? Well, what I mean by that is this. Let me give you an example. Here is a basis in R3, 3 vectors, and I won't show that in here, but this is actually a basis for R3. And this is very easy to show. Just do those 2 steps. Make a linear combination, set that linear combination equals to the 0 vector, and then find those c's, and then those c's would be 0. And then second, show that this set spans R3. Okay, and we did that. I think we did that last time or last week. But anyway, just believe that this set is the basis for R3. Now, my claim here is that if I pick this vector here, let me give you the vector -8, 7, and 17. I can actually write this vector, the linear combination of those 3. So the linear combination is actually 2 times the first vector plus 3 times the second vector plus 5 times the third vector. Okay. So what the uniqueness of basis representation means is that this is the only way you can write a linear combination. There's no other way. So if you ask, okay, I know that this vector here, -8, 7, 17, is written as 2 times the first plus 3 times the second vector plus 5 times the third vector. Do you think that there are other numbers that I can plug in here and get the same vector? So if I put something here, 1, 2, 3, plus something here, 0, 1, 2, plus something here, -2, 0, 1. Do you think if I solve for that, do you think I can find different numbers other than 2, 3, and 5? The answer is no, you cannot. If you solve this, you're going to find 2, 3, and 5. And that's what I mean by uniqueness. Okay, there's only one way to represent a vector as a linear combination of vectors in the basis. And theorem 4.9 proves that. Okay, it's very, very easy to prove. In fact, let me do that here for you. So if let's say I have V1, V2, and Vn, okay, vectors, and let's say that this is a basis for V. Okay, I forgot to say suppose. Okay, suppose this is a basis for V. Now then, the claim is that every vector, here's the claim, every vector in V, in the vector space V, can be written in one and only one way, as a linear combination of those vectors V1 to Vn. Okay, how do we show that? Well, suppose there are two, okay? Suppose there are two representations here. Pick a vector in V. Let's say U, okay? So suppose U has two representations. We know that U has one representation because if this is a basis for V, any vector in V can be written as a linear combination of those, right? Because it's a basis. It's those vectors span the whole space. So let's put here C1 V1 plus C2 V2 plus Cn Vn. Okay, so U can be written as a linear combination of those. Now suppose also that there is another representation. Let's put these now. D V1, D2 V2 plus Dn Vn. Okay, so in other words, U, the vector U that I picked in the vector space V has two representations, two ways of be written as a linear combination of those vectors. Well, now let's subtract, okay? Subtract these two things. So what do I get? Here I get the zero vector, right? U minus U is zero vector. Now what happens if I subtract these vectors here? Well, I can factor them out, right? C1 V1, D1 V1. If I factor V1 out, I get C1 minus D1 V1. Same thing with the second terms. That will be C2 minus D2 V2. And if I keep doing that, then Cn minus Dn Vn. Okay? All right. Now, look at this. What do I have here now? I have a linear combination of those vectors again. See? Something, it's a scalar times V1 plus a scalar times V2. I know it's a subtraction here, but I mean, it's a something times V1 plus something times V2 plus something times Vn. That's equal to the zero vector. Now, because V1, V2, and all those VIs are form of bases, that means that they are linearly independent. If they're linearly independent, guess what? All those coefficients, not C1 only, but C1 minus D1 is 0. C2 minus D2 is 0. All those coefficients are 0. So since V1, Vn are linearly independent, right, because they're bases, because they form a basis. So what we have is that all those coefficients, C1 minus D1 is 0. C2 minus D2 is 0. Okay, the coefficients here are not C1 only, it's C1 minus D1. This is one coefficient. Here's the other coefficient, C2 minus D2. So they're all 0. And therefore, because they're all 0, it means C1 equals D1, C2 equals D2, and Cn equals Dn. So what we showed is that if I have a different representation, well, if I have another representation, well, those DIs, they better be equal to CIs. And that's what we see here, okay?